there are certain conditions that have to be satisfied to be able to arrive to such a universe which is composed of matter, but there is no antimatter at all. And one condition concerns the CP violation. That is to say, under charge conjugation and space parity, when you apply charge conjugation times space parity to a physical system, you should find certain asymmetric terms, certain terms which change their sign, whatever, so that there is a net amount of asymmetry created in course of the evolution of the universe. And that has to be tackled, because the CP violation, whatever it is, if it exists in the system, has to be understood in terms of fundamental particles, which I mean protons, quarks and leptons. We have to understand if they have certain CP violating or plane violating interactions among them. I will not again speak about this thing, but when I go to supersymmetric models, I will start speaking about this issue, and then I will give a, let's say, a little bit more detailed definition or the explanation of the story. However, question is, these are the questions to be answered for sure, but there is one more subtle question which concerns both of these points as well as some other stuff that I will mention. The question is this: what will come next? We don't know this. Okay? We have come down to quarks, where we know that leptons are fundamental particles, they are here, but we don't know what's coming next. We are at the scale of 10 to minus 18 meters, and we don't know what will come next, because the next scale, so to speak, is 10 to minus 21 meters, which corresponds to zetometer. Zetometer scale is something like 1 TeV to 10 TeV scale, let's say 10 to 100 zetometer scale. So we want to find the answer to this question. Higgs sector, that I will mention soon, is one of the tools or one of the driving machines for looking for or for constructing or for understanding new physics models. The models that concern this region. We don't know this domain, we don't have much clue to see or to expect what to find here, and this sector is one of the driving machines for looking for or for understanding or for, I don't know, for postulating some models, some mechanisms, some particle spectrum in this domain. Hopefully we will find them in the LHC. To understand things from first principles, let's look at the conversion to the nuclei. You see here photography, and I don't know, it can destruct your cells, other stuff, which I don't know at all. I mean, this is the process which gives you atomic bomb. This is the atomic bomb. It exists, it is in the nature. It is everywhere, it's around. I mean, the way to explain this process is like this. According to Fermi, let's say, I mean, it's not actually Fermi's model, but we are a little bit somewhat enhancing Fermi's model. Neutron, which is composed of two d quarks and a u quark, is getting converted into proton, which contains two u quarks and a d quark, and meanwhile, for conservation of energy, for conservation of angular momentum, for conservation of electric charge, they are giving off certain particles. And here in this simple picture, I am showing you an electron is given off, and then electron is given off as well. And here, the story is that there is a massive particle exchanged in this process. This massive particle is supposedly a vector particle. This is to say, we do have a vector boson here. But what is important is that this vector boson is massive. Understanding a massive vector boson is very, very difficult. Of course, the most difficult one is a massive graviton, but massive vector boson is also quite non-trivial, quite difficult thing to understand. We will see why it is. But essentially, let me summarize for you. In nature, we know that uranium and all other unstable nuclei get converted into lesser and smaller nuclei, and this happens with a certain amount of lifetime. And such processes can be explained with such a Feynman-like diagram or Feynman diagram, let's say. This is just a picture, this is just an imagination. And what's happening is that, according to Fermi's original approach, where he wrote an effective interaction instead of W's mass, he put Fermi coupling, and he found that this interaction occurs with the coupling between two vector currents. Not tensor currents or not scalar currents. Two vector currents were required to understand this. And it is that they had vector currents coupled to each other via the exchange of a vector via some particle. This particle has to be a vector boson. Moreover, it has to be a massive vector boson to be able to explain Fermi's original model where he wrote down Fermi coupling for such an interaction. So, we have to understand the massive vector boson. The issue is quite non-trivial actually. It's not easy to say that I write, for instance,